And the heat of formation, or delta H formation here, is equal to the heat of, or the enthalpy of reaction if we're talking about forming 1 mole of compound from its pure elements, which are in their standard states. So basically, there's a table that you can look up which tells you the enthalpy of formation for any compound that you're interested in. And this is actually in Appendix 2 of your textbooks, and you will need to use this to solve your problems on the P set. But let me say that, for example, if we're talking about water here, that's formed from hydrogen and oxygen if we're talking about the elements in their pure forms at 1 bar standard states and room temperature. And if we look this up in our textbook, we would find that the delta H of formation for water is negative 286 kilojoules per mole. Similarly, we can look up the same thing, for example, for carbon dioxide. And what we'll find here is that our delta H of formation that we look up is negative 393.5 kilojoules per mole. We can also look up or think about what our delta H of formation would be for oxygen. Does anyone have a guess here? Yep, it's actually going to be 0. Oxygen already is in its most stable state. So anytime we're talking about an element in their most stable state, it's going to be 0. That's going to be the delta H of formation. There is none. It's 0. We can also look up what it was for sugar, for glucose, C6H12O6. So that coming from its most stable forms, its most pure form of the elements, is going to be negative 1,260 kilojoules per mole. All of this information has been tabulated and is in tables. You can refer to them, and they're also in the back of your textbook, so you can refer to those in terms of your problem set. So let's go ahead and solve a problem actually using the delta H's of formation. Let's see if we can do any better to coming close to the reality for the oxidation of glucose. So if we're going to calculate the delta H for the reaction for the oxidation of glucose, or actually for any reaction at all, what we want to do is take the delta H of formation of the products and subtract from that the delta H of formation of the reactants. So let's go ahead and do that. And in terms of talking about the oxidation of glucose, if we talk about delta H of this reaction, what we need to take is 6 times delta H of formation of CO2, since we're forming, that's in our products, we're forming 6 moles of CO2, plus 6 times delta H formation of H2O, since we're forming 6 moles of H2O, and we subtract from that the heat of formation of all of our reactants. So we only have 1 mole, so we just say delta H formation of C6H12O6. And then in addition to that, we have 6 moles delta H formation of oxygen, of O2. All right, so this is our equation here. And at this point, what we would do is we would look up what all of the delta H formation values are for CO2, H2O, sugar, and oxygen. So what we would find is that we end up having 6 times negative 393.5. That's what we had just looked up and told you for CO2, plus 6 times negative 285.8 for the water, minus 1 times 1260. So it's negative 1260 for our sugar here. And then what we're going to end up with is having minus, and what is it for oxygen again? So minus 0. So what we end up with in terms of the delta H for the entire reaction here is that we end up with negative 2816, and it's going to be kilojoules per mole of glucose. All right, so let's see how this matches up, and hopefully you can actually remember that this matches up actually perfectly here. So what we're going to see is that, in fact, what we calculated versus what is experimental is dead on the same. So there's actually one more way to figure out the enthalpies of a reaction. I'm going to go over it just very briefly. And that's based on the fact that enthalpy is a state function. And by state function, what I mean is that it doesn't matter how you got from point A to point B. All that matters is the difference between the two.